This is the lecture for chapter 20, but I have divided it into two parts. So this is going to be part 1 of chapter 20, carboxylic acid derivatives. Alright, let's start with the relative reactivity of the different derivatives of carboxylic acids. We have seen this resonance before. This is not the first time that it's actually presented to us. So we have an L atom attached to the carbonyl, and we can delocalize a lone pair of atoms towards the carbonyl, and then we can of course break the double bond of the carbonyl and give the electrons to the most electronegative element, and we get this other resonance structure right here. This is an equilibrium, of course, and depending on how much L can actually donate to the carbonyl, I can get a lot of this resonance structure, or maybe I won't get a lot of that resonance structure. So I have nitrogen, oxygen, and we have a chloride right here. Fluoride, of course, is there because that's the little corner of our periodic table. And nitrogen is not as electronegative. It means that it can donate to the carbonyl a little more than the oxygen would be willing to donate. And both of those can donate more than the chloride will be able to donate. So if you have a nitrogen attached to the carbonyl, you have a lot of this resonance going on. If we have an oxygen, we have a fair amount of the resonance still happening. But if you actually attach a chloride where L is, then we will not have a lot of that resonance going. So now at the very end, right here, I have amides. So I have amides right here. Those are not going to be as reactive as the esters, because the nitrogen can donate more than the oxygen to the carbonyl. This is an ester, and even though the ester, the oxygen of the ester can donate, it is not as willing to donate as the nitrogen. Then over here we have your acyl halides. When I say that, we're mostly going to be using the chloride, so I'm going to put acyl chlorides right here. The chloride will not donate to the carbonyl, so we don't have a lot of this resonance happening. So the carbonyl of an acyl chloride is going to be our most reactive carbonyl. Now all the derivatives of carboxylic acids can be converted back to the carboxylic acid, and this is basically what we have. Here's our derivatives of carboxylic acid. At the very top I have the acyl chloride. That's going to be our most reactive carbonyl, and we can prove that because in the hydrolysis with water, if we do it at 20 degrees Celsius, the reaction is going to be fast. Notice I get the carboxylic acid. This is an anhydride. It's the second most reactive carbonyl. When you do the hydrolysis, though, at 20 degrees, we notice that the reaction is not as fast as the acyl chloride reaction. The reaction kind of slows down. Still, if you let it go for a longer time, you still get the carboxylic acid. Now here's the esters, and in terms of reactivity, the esters are less reactive than anhydrides, and the anhydrides are less reactive than the acyl chlorides. And we can show you that it's less reactive because under the same hydrolysis conditions, the reaction is going to be very slow. The last one, the least reactive carbonyl, is our amides, and it's going to be an extremely slow reaction. So I need you to remember this order right here, because the order is an increase in reactivity. So that's why I need you to remember the reactivity of the derivatives of carboxylic acids. Another thing that's very important in here is that the conversions that I can make are all based on what they have underneath them. So it's important that you remember this order. So the acyl halides, acyl chlorides being the most reactive carbonyls, I can convert them to the anhydrides. I can convert an acyl halide to the ester, or I can actually convert the acyl halide to the amide. However, I cannot go back in reactivity, back up in reactivity. So if I have an anhydride, I can make the anhydride into an ester, or I can make the anhydride into an amide, but I will not be able to go back up in reactivity. So I cannot make an acyl chloride out of an anhydride. The ester, now the reactivity is kind of really limited. I can make an amide, I can make the carboxylic acid, and I'm going to show you a couple more reactions. But if you have an ester, you will not be able to make the anhydride, and you will not be able to make an ester into an acyl chloride. So again, think of this as a ladder. You can climb back down, but you cannot go back up. Let's start with the acyl chloride reactions, then we do two anhydride reactions, then the esters, and we'll close the chapter with the amide reactions. Excellent. Think of this as a spider, but this one kind of goes down. All right, let's start right here. We are going to be doing an acyl substitution reaction. So we're substituting the chloride for something else. So if you actually add water, we are going to end up with a carboxylic acid. So this is the hydrolysis reaction that we were talking about, and at 20 degrees this is going to be a fast reaction. If you add a carboxylic acid, if you add a carboxylic acid to your acyl chloride, you're going to get an anhydride. The anhydrides are right underneath the acyl chlorides, so we can still make them in pretty good yields. If you add an alcohol, then this oxygen would attack the carbonyl, form the tetrahedral intermediate, and displace then the halide. So we're going to make an ester out of our acyl halide. You don't actually have any type of limitation on the alcohol. It can be a primary, a secondary, or a tertiary alcohol. This one right here, with the reaction of an amine, you can actually make amides out of this. This one does have a limitation because I can actually add ammonia or a primary amine or a secondary amine. This reaction will not happen with tertiary amines. Last but not least, this is a good reaction right here, so I want you to know it very well. This is an organocuprate, and we have seen them before. And the organocuprate has two carbon groups attached to a copper one, and there's a lithium in there as a counter ion. But notice a reaction. We're going to substitute the chloride for one of the groups on the copper. So we make a ketone out of this. And this is a very handy dandy reaction because you can start with an acyl chloride. You can take a carboxylic acid, make it into an acyl chloride, and then you can make whatever whatever ketone you want. This can also happen with Grignards. So you can take an acyl halide that you want, and you can add a Grignard. Let's add phenyl magnesium bromide. And we're basically going to put a phenyl in place of the chloride. We're going to do a nucleophilic acyl substitution. You would go through the tetrahedral intermediate, but the chloride is an excellent leaving group, so it will leave when you reform the carbonyl. And that way, you can, in one step, go from an acyl halide to a ketone. So you can use the organocuprates, or you can use Grignards for that reaction. It's a very important reaction, and I expect you to actually know it and remember it. Now we're going to actually draw the mechanism for the conversion of propanoyl chloride with ammonia. So we have propanoyl chloride, three carbons and the chloride right there. And we're going to do this reaction with ammonia. We are going to need a little bit of excess of ammonia. We're going to need at the very least 2 equivalents of ammonia. The reaction is actually done using water as solvent, and it goes really nicely at 0 degrees, so it's a fast reaction because your carbonyl is the most reactive carbonyl that we have. All right, let's start the reaction. I have a really good nucleophile there. Well, maybe not a very good nucleophile, but a nucleophile nonetheless. And it's a good nucleophile. It attacks the carbonyl, which is a really nice partial positive carbonyl. We get our tetrahedral intermediate. Now when the ammonia attacked, it had 3 hydrogens with it, so at the beginning it's going to be positive, but of course we're going to actually deprotonate this one, and here's where you actually need the excess of ammonia, the second equivalent of ammonia, because we're going to deprotonate with the excess ammonia. We're going to deprotonate our tetrahedral intermediate. When we're when we're losing a proton, I'm going to put minus a proton right there. And now I have a neutral nitrogen at the bottom. The oxygen is still negatively charged, but now I have only 2 hydrogens there. The ammonia right here was converted to NH4, the ammonium salt. But here's our tetrahedral intermediate, and I have a good leaving group in there. So the chloride is a good leaving group. The way that we're going to make it leave is by reforming the carbonyl and kicking out the chloride. That takes you to your amide. So this is basically the mechanism for every nucleophilic acyl substitution that we're going to see. We attack the carbonyl, get the tetrahedral intermediate. In the case of the derivatives, the tetrahedral intermediate will have a good leaving group, and you reform the carbonyl to kick out the leaving group, and you will get your derivative. Remember that for this reaction, you will need at least 2 equivalents of ammonia, or the amine that we're using. All right, let's keep going on our lecture. Let's see what's next. Oh, this reaction you have seen before right here. When you have an acyl chloride, you can reduce it with lithium aluminum hydride. Remember, lithium aluminum hydride is a reducing agent. And it has 4 hydrides, so there's plenty of hydrides to go around. I say that because when you have an acyl chloride, you're going to attack with 2 hydrides, and that will afford you the primary alcohol. So go ahead and attack with 1 hydride, get a tetrahedral intermediate. I'm just gonna attack, get a tetrahedral intermediate. It has the chloride. The chloride is a good leaving group. That's just an extremely thick single bond. I am sorry I did that. And then you remake the carbonyl by displacing the chloride. Notice that we have an aldehyde intermediate. We do not isolate the aldehyde intermediate because we still have 3 more hydrides in our lithium aluminum hydride. So a second hydride attacks. We get a second tetrahedral intermediate. And this time around I don't have any good leaving groups, so the only things left to do would be to actually work up the reaction. I call it quenching, some people call it working up. So you quench the reaction and you protonate the oxygen and you get your primary alcohol. Now I have a different type of lithium aluminum reagent. It's a modified lithium aluminum reagent, and notice that I still have the lithium and the aluminum, but 3 of the hydrides have been replaced for turbotoxic groups. I only have 1 hydride in this reaction, and if we only have 1 hydride, I can actually do the first step on this reaction and I can get an aldehyde out of that. Can you think of another reagent that we have discussed that does the exact same reaction? If you thought about Dibal, then you're perfectly fine. Dibal can actually do the exact same reduction. So we'll take an acyl chloride. We have seen it with esters, but it will reduce your carbonyl to the aldehyde. Now I don't actually cover anhydrides quite a